Welcome to the video lecture series on digital electronics. In the previous lecture, we discussed about how to convert the decimal numbers into other base, that is, into binary, octal, and hexadecimal, and the conversion of other numbers into decimal as well. In this lecture, we are going to discuss about the conversion of binary numbers into octal and hexadecimal and vice versa. That is the conversion of octal and hexadecimal numbers into binary. Let us first discuss the conversion of a binary number into octal number system first. So each octal number, that is 0 to 7 numbers, are represented by a 3-bit binary equivalent as shown in the table. So here there are 0 to 7 octal digit. Each octal digit is represented by its 3-bit binary equivalent. So each octal number can be converted into 3-bit binary equivalent. So because the maximum digit in the octal number system is 7, and for to represent 7 in binary, 3 bits are sufficient. For this reason only, each octal digit is converted into 3-bit binary equivalent. So to convert a binary number into octal, the integer part of the binary number and the fractional part of the binary number, both the integer and fractional numbers to be converted into octal. So first, to convert the integer part of the binary number into octal, scan the binary number from right to left, that is starting from the decimal point towards the left hand side, and partition the binary number into each 3 bit. First, we scan the binary number from decimal point towards the right side and partition the binary number into 3 bits each, and write down the 3-bit binary equivalent of each octal digit. So after partitioning the binary number into 3 bits each, write down the octal equivalent of each 3-bit binary, each 3-bit binary number. If any of the partition is less than 3 bits, add zeros. For the fractional part, to convert a fractional part of the binary number into octal, scan the number from the decimal point to the right side, that is from left to right, and partition the binary number into 3 bits each. After partitioning, translate each group of 3 bits into corresponding octal digit. So while partitioning, any of the partition is lack of 3 bits, add zeros. So let us take an example of binary number and convert it into octal equivalent. So first to write down the given number as it is. So in this case, the given number is 1 0 111.01101. So this is the binary number which contains both integer part as well as fractional part. So the first step in the conversion process is partition the binary number or scan the binary number from the decimal point towards the left hand side and right hand side. That is, partition the binary number into 3 bits each from the decimal point. So that is, so partitioning this number from the decimal point towards the left side, this is my first 3 bits and remaining is the 3 bits. At the same time, partition the fractional value of the binary number into 3 bits each starting from the decimal point. This is the first partition, and for the second partition there is only 2 bits, so we can fill the third bit with zeros. After partitioning the binary number into 3 bits each, write down the octal equivalent of each 3-bit binary number, which is explained in the previous slide table. So G101, so for the 101 3-bit binary, the equivalent octal digit is 5. 110, that is equivalent to 6. 0.011, that is equivalent to 3. 010, that is equivalent to 2. So after converting this given binary number into its octal equivalent is 56.32 base 8. This is how we will convert a binary number into its octal equivalent. Simply partition the binary number from the decimal point towards right side and left side into 3 bits each. After partitioning, write down the 3-bit octal equivalent of each binary digit. So that gives you the octal equivalent of the given binary number. Let us see how to convert a binary number into its equivalent hexadecimal number. So to convert this procedure, to follow this procedure, we required the 4-bit binary equivalent of each hexadecimal digit. So the below table gives you the 4-bit binary equivalent of each hexadecimal digit. So in hexadecimal number system, total there are 16 digits are there. So each one of these 16 digit is expressed into 4-bit binary equivalent. As we all know that A stands for 10, so the binary equivalent of 10 is 1010, and the binary equivalent of last digit F in the hexadecimal number system is equivalent to 15. So the binary equivalent of 15 is 4 ones. So in this case, each hexadecimal digit is represented by its equivalent 4-bit binary number. So why 4-bit? Because if you observe, the maximum digit in the hexadecimal number system is 15. That is, we represented in F. In order to represent 15 in binary, 4 bits are sufficient. For this reason only, each hexadecimal digit is represented in binary by its equivalent 4-bit form. Now coming to the conversion part, there are two steps are there. We will convert the integer part and the fractional part. So to convert the integer part of the binary number, so first scan the binary number or observe the binary number from the decimal point towards the right side and partition the binary number into 4 bits each. We need to partition the binary number into 4 group of bits and translate each 4-bit binary number into its hexadecimal digit from this using this table. If any one of the partition is lacking of 4 bits, add zeros. So we can add zeros to make it into 4-bit equivalent. In a similar manner, we can convert the fractional number into its equivalent hexadecimal, partition the number from the decimal point towards the right side into 4 bits each. So the binary number is partitioned into 4 bits each, and translate each 4-bit group into its corresponding hexadecimal digit by using the table. And if any one of the partition is lack of 4 bits, add zeros. So let us see one example how to convert this binary number into its equivalent hexadecimal digit. Consider the example given a binary number. So the first step is to write the binary number first, that is 1011.011.01101. So this is the given binary number. So the first step is to partition the binary number starting from the decimal point towards the left hand side and towards the right hand side. So partition the binary number into 4 bits each. So this is my first 4-bit partition, and the remaining 4 bits, there are 4 bits, so there is no need to add any zeros. So for the fractional part, starting from the decimal point towards the right side, partition into 4 bits each. This is the first 4 bits, and this is the next 4 bits. Two partitions are there. If you observe, the third partition is having only one bit, that is only one digit. So in order to make it into 4-bit partition, add 3 zeros. Now write the hexadecimal equivalent of each 4-bit binary number. So the first binary number is 1011, that is nothing but 11. So 11 in hexadecimal number, it is equivalent to B. So next 1110, so that is nothing but E dot 0110, that is nothing but 6. Again 1110, that is E, and 1000, that is nothing but 8. Right? You can get the 4-bit binary equivalent of each hexadecimal, which is explained in the previous slide table. So in that table, each hexadecimal digit is represented in its 4-bit binary equivalent. So after converting this value, so the hexadecimal equivalent of the given binary number is BE.6E8 base 16, because this is an hexadecimal number, so its base is 16. Right? So this is how we will convert a binary number into hexadecimal. The procedure is very simple. Partition the binary number starting from the decimal point towards the left hand side and right hand side into 4 bits each, and write down the hexadecimal equivalent of each 4-bit number. Now it is possible to convert the octal and hexadecimal numbers into binary. So let us see how to convert an octal number into binary. So to convert an octal number into binary, simply write down the 3-bit binary equivalent of each octal digit. That is, for example, let us convert the octal digit 76.21 into its equivalent binary. So this is the octal number. So in order to convert this octal number, write the 3-bit binary equivalent of each octal digit. The first octal digit is 7. The binary equivalent of 7 is 3 ones. Next octal digit is 6, and its binary equivalent is 110 point. The next octal digit is 2. The binary equivalent of the 2 is 010, and the next octal digit is 1. The binary equivalent of 1 is 001. So this is how you will convert your octal number into binary by writing 3-bit binary equivalent of each octal digit. In a similar manner, we can convert a hexadecimal number into binary as well by writing the 4-bit binary equivalent of each hexadecimal digit. For example, let us take an hexadecimal number A21.38 base 16. So this is an hexadecimal number. In order to convert this hexadecimal number into binary, write the 4-bit binary equivalent of each hexadecimal digit. So in this number, the first hexadecimal digit is A, right? So A is nothing but 10. So the binary equivalent of 10 is 1010. Next hexadecimal digit is 2, that is 0010. Next hexadecimal digit is 1, that is 0001. There is a decimal point dot. The next hexadecimal digit is 3, that is 0011. And the last hexadecimal digit is 8, that is 1000. Base 16. This is how we will convert the hexadecimal number into binary. Thank you.